Hello everyone. In our previous lectures, we have discussed about different components of optical fibers, how the information travel from one end to other through an optical fiber. What is the basic principle behind the propagation of a signal from one point to other through an optical fiber? Then what are the different parameters which are deciding the propagation of information from one end to other? After that, we have discussed critical angle, acceptance cone, numerical aperture, and all those parameters which are the deciding factors in case of optical fibers. After that, we have discussed about different types of optical fibers like step index optical fibers and graded index optical fibers. Then after that, now we have our next topic, that is losses in optical fibers. So attenuation and signal losses in optical fibers, they are because of different factors. As I have told you, in case of multi-mode step index optical fibers, the different modes, they were reaching over the receiving end at different times. So when different modes, they were reaching over the receiving end at different times, so there was a dispersion of the signal, and that dispersion is known as modal dispersion. And if there will be stretching of that particular signal at the output end, so that signal will get overlap, and you cannot get the exact information which is transferred from transmitter to receiver. So that was a limiting factor, because of which the multi-mode step index optical fibers, they were not able to carry the information up to long distance. So there are many factors which are responsible for signal losses, because of which the input which we are providing at the transmitting end, that is not exactly transferred to the output end. So basically this energy loss, this power loss in optical fibers, that is known as attenuation. And this power loss is denoted, that is basically expressed in terms of decibel. So the power loss in decibel is -10 log of output power upon input power. So this minus sign, that signifies loss here, and this P input, that is the input power, which is the power at transmitting end, and the output power, that is the power of that optical signal at the receiving end. This power loss per unit length, that is expressed in decibel per kilometer. So whenever we want to express this power loss or energy loss or this attenuation, that will be expressed in decibel per kilometer, and it is known as, this term is known as attenuation constant. This attenuation constant is denoted by alpha, which is -10 upon L log of output power upon input power. So this is power loss per unit length. It means it is expressed in decibel per kilometer. So there are different factors which are responsible for the signal losses. The first one is absorption. So when the light signal, when the information which is moving from transmitter to receiver in the form of optical signal, in the form of light, then that light can be absorbed either by the fiber material or that can be absorbed by certain impurities which are present in that material. So whenever that signal will be absorbed because of any reason, then the information carrying capacity, or there will be loss of that signal. So this absorption is that absorption plays a very important role for the signal losses. So it is a very much contributing factor. Second one is scattering. So when light is traveling through the core, it can get scattered by impurities or small region with sudden change in refractive index. So if this is an optical fiber, and if there are certain impurities in this optical fiber, so when light will strike over that impurity, then light can get scattered from, if it is absorbed, then that signal loss will be due to absorption. But if the light is striking over that impurity, and if light will get scattered, then that type of loss is known as scattering loss. So light traveling through the core can get scattered by impurities or small region with sudden change in refractive index. So there is one term known as Rayleigh scattering. So Rayleigh scattering, that inversely proportional to lambda raised to power 4, and it plays a significant role in power loss in optical fibers. There is one more factor which is known as radiation loss, which is responsible for signal losses. These losses are due to change in angle of incidence at core cladding interface due to bending of cables. So if you have an optical fiber, and if it is not in the same, if it is bent at certain point, then at that particular point there will be a change in angle of incidence. And if at that point where that optical fiber is bent, if at that point angle of incidence is less than critical angle, then that signal will not travel from transmitting end to receiving end. That will escape from the optical fiber, that will be absorbed by the cladding. So this particular factor, radiation loss, that will also contribute in signal losses or in attenuation of in optical fibers. So whenever you want to find that signal loss or attenuation for optical fibers, you can find with the help of this particular formula, equation number 1 and equation number 2. So now we have two examples here. First one is the optical power of 1 milliwatt that is launched into an optical fiber of length 100 meter. So you have an optical fiber with length 100 meter, and over the input end the optical power is 1 milliwatt, and at the output end we are getting only 0.3 milliwatt power. So we have to find the attenuation. So that attenuation constant is minus 10 upon L log of output power upon input power. Since length is 100 meter and since the signal loss is in decimal per kilometer, you have to express this L in kilometers. So you have to convert 100 meters into kilometers. So that is equal to 0.1 kilometer, and rest you have to substitute input power and output power. You will solve it and you will get that attenuation constant in decibel per kilometer. One more example is there. An optical fiber of length 150 meter has an input power of 10 microwatt and output power of 9 microwatt. You have to find the loss in decibel per kilometer. Again, same formula, minus 10 upon L log of output power upon input power. After solving, you are getting this loss in decibel per kilometer. So that's it about signal losses or attenuation in optical fibers. Thank you.